In this video, we're going to talk about how to find the inverse of a 2 by 2 matrix. I'm going to start with what you see on the screen here. I've got a matrix. We could call this one A and this one B. And this one clearly is I, the identity matrix, dimension 2. And I'm going to do A times B equals the identity matrix. The problem is what I'm looking for here is the inverse, A times A inverse. In fact, let's go ahead and rename this. Instead of B, we'll call it A inverse, because that's what we're after, and that's what this particular multiplication will do if what the result is the identity matrix. So how might we go about doing this? Well, if what we're looking for is what the entries in the matrix are, then we could just call those, for example, A, B, C, and D, and then we'll perform this matrix multiplication, which will give me 2 times A plus 1 times C, 2A plus C. And we know that the result of that multiplication has to be, this is row 1, column 1. So this row 1, column 1 entry in the answer is 1. And then we'll do that for the other entries over here. We'll have 2 times B plus 1 times D, and that's going to equal 0. 2B plus D equals 0. And then my second row, through negative 3 times A plus 0C. So negative 3A plus 0C equals 0. And lastly, negative 3 times B plus 0D, negative 3B, and that's going to equal 1. So negative 3B equals 1. And from this, I can take the two equations that have A and C in them and create a system of equations. 2A plus C equals 1, and negative 3A equals 0. And I'll use a different color. The two equations that contain B's and D's, and that will give me, let's see, 2B plus D equals 0, and negative 3B equals 1. And then what I'm going to do is I'm going to solve each of those systems of equations to figure out what A and C are here and what B and D are here. And then I'll have the values that go with A, B, C, and D, and I'll have my inverse. So that's the process. I'll go ahead and see that out so that you can see what the result is. Get rid of some of this extraneous scribbling. I'm notorious for not leaving myself enough room to do things. In this particular problem, we're kind of in luck because it's really super easy to see here that this is going to give us A equals 0, right? I mean, in order for anything, any product to equal 0, this unknown, this can't be 0, negative 3 can't be 0. So this, if the product is 0, then A must be 0. There's only one way to get that. You might not always have such a nice gap in your system here. You might have had, say, for example, negative 3 plus 2C equals 0, and then you would have to actually have worked out what A and C were using more conventional methods for solving systems. In this case, we got lucky. And if I know that A is 0, then I can replace this A with a 0, and I get 0 plus C equals 1, or C equals 1. And then I'll do the same thing for the other two entries, the other two values. I'll start with this one because, again, it's the easiest, but it's not quite as straightforward because in this case, what I'm going to have to do is divide both sides, because my right-hand side is 1 here, not 0. Divide both sides by negative 3, and I get B equals negative 1/3. But now that I know that B equals negative 1/3, I'll go down here and I'll say that's 2B plus D equals 0, but where B is negative 1/3. So I have negative 2/3 plus D equals 0. So D equals 2/3. 2/3. So now I have all four values for A, B, C, and D, and that tells me that the matrix I was looking for, A inverse, instead of being equal to A, B, C, D, is equal to 0, negative 1/3, 1, and 2/3. And there's my inverse. Now, this is a good, solid, generic approach to finding the inverse of a 2x2 matrix. There's a shortcut, and I'm going to explain that shortcut in just a minute. But I want to point out that the process that we've just performed here is the reason the shortcut works, right? We'll see in a minute that there's a pattern to the numbers in the original matrix A and the matrix A inverse. All the same numbers appear in there, and there's a reason for that. And so I'm going to do, actually, I think what I'll do now is show you the shortcut, and then we'll use that to confirm that the work that we did down here to get this inverse result will, the shortcut will result in the same inverse matrix A. So I'm going to do an experiment here. Can I shrink this? And I don't know if that'll show on the screen, but I'm going to give it a try. I want some more space to do this work. So the first thing I'm going to do now is, or the next thing I'm going to do is I'm going to write out the shortcut for finding the inverse of a 2x2 matrix. And that is that if I start with a matrix A, the letters that are used in the textbook here are A, B, C, and D. And so this might be a little bit confusing in that I used, just because this is how I learned how to do this, I used A, B, C, and D for my as at that point unknown inverse matrix. And here I'm using A, B, C, and D for my matrix A. Make it a little bit neater. So be aware as I go through this process that this A, B, C, and D is not the same as the A, B, C, and D I had over here. This was for my inverse. This is for my original matrix A. And if we say that A is equal to this, then we'll be able to find A inverse using this little algorithm. Take 1 and divide it by AD minus BC and multiply that by the matrix. A, B, C, and D are all going to be in there, but we're going to reverse the positions of A and B, or sorry, A and D, not A and B, A and D. So instead of A in the top left and D in the bottom right, those two are reversed. And B and C are going to stay where they are, but we're going to negate them. And the result of this scalar multiplication of a matrix will produce the same A inverse as we got when we did it by hand. So let's go ahead and do that for our matrix A here. We're using this matrix A because we want to test this algorithm to see if we get the same result as we did here. And in that case, my A is 2, my B is 1, my C is -3, and my D is 0. So I'm going to have 1 over A times 0 is going to be, or A times D is going to be 2 times 0. And I'm going to subtract B times C, which is 1 times -3. Let's see, I think I'll just write that as -3. 1 times -3 is -3. And then I'm going to multiply that scalar by D was 0, so that goes there. A was 2, so that goes there. B was 1, that becomes -1. And C was -3, and so that becomes +3. This is 1 over 0 plus 3, so 1/3, times the matrix 0, -1, 3, and 2. And that gives me, this is just a fraction, this is just a scalar. So I'm going to have 0, -1/3, 3 over 3 is 1, and I get 2/3. So as you can see, that is the same matrix as I got by doing it the long way, if you will. I think with a 2x2 matrix, it's almost about the same amount of work between these two. I don't know, this is maybe slightly easier. The thing is, it only works for 2x2 matrices. And if you forget the formula, if you forget the algorithm, then all you have to ask yourself is, well, what is an inverse matrix, and how could I find these 4 values if I knew what an inverse matrix was and what it does, what it produces? Then all you need to do is this relatively simple process. So this shortcut is nice if you remember it, but it's not strictly speaking necessary. One thing to be aware of, and one thing that this method is helpful for, is that if this value here is undefined, if AD minus BC is 0, then we can't find this matrix. We can't find A inverse. So that just doing this part of the computation may tell us something about the invertibility of the matrix A.